For the second part, we're going to be looking at what's called uniform motion or distance problems. And these problems come in three basic types. One is you have two objects, planes, cars, trains, whatever, that are leaving from the same point going in opposite directions. And your equation is made talking about the total distance. In that case, the distance that the first one travels plus the distance that the second one travels is equal to the total distance. So distance of 1 plus distance of 2 is equal to the total distance. A second possibility is you have something that leaves, a car, a train, a person, whatever, and somebody else leaves later than that, and you talk about when will they catch up with this one. Well, in that case, the distances that they travel are the same because one catches up with the other one. So in that one, your equation is made by taking distance 1 is equal to distance 2. A third possibility is when you go and you come back. And in that case, again, the two distances are the same. So your equation is made by setting the two distances equal. So it'll be helpful if you're looking at the problem in the book. And we're going to start, it's on page 141. And we're going to start with problem number 27. So I would suggest that you pause the video and stop and read the problem for a minute. Just like with the mixture problems, a little chart helps us organize our information. And in problem number 27, we're talking about a boat going up and down the river. So it talks about the boat going upstream and then coming back downstream. Upstream, downstream. And what we know, not because the problem tells us this, but just because we know this for a fact, when a boat travels upstream, the current slows it down. So it's the boat minus the current. When a boat travels downstream, the current speeds it up, so it's the boat plus the current. And that holds true anytime you've got something going upstream and downstream. You go on and read in the problem, and it tells us that the boat by itself can do 16 miles per hour. So these two become 16 minus C and 16 plus C. It also tells us that the time for going upstream was 20 minutes. Now, since this rate is given in miles per hour, we have to make the time be in that same unit. So 20 minutes is 20 sixtieths, or 1/3 of an hour. The problem tells us that when he goes downstream, it takes 15 minutes. So that's 15 sixtieths, or 1/4 of an hour. To complete the distance column, you never have to look at the problem. This information does not come out of the problem. It comes straight from here, multiplying the rate and the time together. So I'm going to take the 1/3 and multiply it by the 16 minus C, and I'm going to take the 1/4 and multiply it by the 16 plus C. Now I have to decide which one of these three scenarios it is. And in this case, the boat is going upstream and then coming back downstream, so that the two distances have to be the same. So I'll take these two distances, 1/3 times 16 minus c, and 1/4 times 16 plus c, and that's how I get my equation, making those two distances equal. Now I'm going to multiply 1/3 times 16 and get 16 over 3, 1/3 times c, 1/4 times 16 is 4, and 1/4 times c. Our life will be easier if we clear the fractions. I see that my denominators are 3 and 4, so I'm going to multiply every term by 12. When I multiply 12 times 16 over 3, I get 64. 12 times 1/3 is 4 times c. 12 times 4 is 48. And 12 times 1/4 is 3 times c. Now I'm going to get my c's on the same side of the equation, so I'm going to subtract 3c so that those will zero out. Then I'm going to subtract the 64. And then I'm going to divide by the -7. Negative divided by negative will be a positive. Now, typically we leave answers as improper fractions. But when you do a word problem, you typically do not do that. When you were talking about the rate of a current of a river, you wouldn't normally say it's 16/7 miles per hour. So we've got two choices. We can convert it to a mixed number and make it 2 2/7 miles per hour, or we can convert it to a decimal by dividing 16 by 7. That's what the back of the book does, and they actually carry it out to 3 places. Now, if I weren't looking in the back of the book, I'd probably just carry it to 1 and do 2.3 miles per hour, because again, we don't typically say, oh, he was going 2.286 miles per hour. But what my math lab will do, I'm not sure. You're just going to have to read and see, do they want it as a fraction or do they want it as a decimal? All right, our next problem is going to be number 47. And in problem number 47, we've got two guys running around a track. So we have Mike and Dan. Now you need to read the problem so that you can understand where I'm pulling this information from. The problem tells me that Mike can run 1 mile in 6 minutes. That gives me his rate. A mile per minute is a rate. So he runs 1/6 miles per minute. The problem also tells me that Dan can run the mile in 9 minutes. So he can run 1 mile in 9 minutes. So his rate is 1/9 miles per minute. So I'm going to fill those in up here in my chart. Mike's rate is going to be 1/6 mile per minute, and Dan is going to be 1/9 mile per minute. Now let's look at time. All it tells me in the problem is that Mike lets Dan start a minute ahead of time. So here's what's happening. Dan starts. 1 minute later, Mike starts. And the question is, when does Mike catch up with Dan? Now, one of these has to be X and the other one has to be in relationship to that. You could do that Dan is X and Mike is X minus 1. That would work. Or you could do that Mike is X and Dan is X plus 1. The point is, Dan's time has to be 1 minute more than Mike's time because he got a minute head start. Now in the last problem, I converted minutes to part of an hour. This time I'm not, and the reason is right here. My rate is given per minute, so my time needs to be measured in minutes. So I'm going to call Mike X and Dan X plus 1 because Dan ran a minute more than Mike did. Those don't line up. Sorry. This should be 1/6 and this should be 1/9. I don't have them on the same line. There we go. So to get the distance, I'm going to multiply straight across. 1/6 times X and 1/9 times X plus 1. Because Dan runs and Mike catches up with him, they travel the same amount of distance. So I'm going to take those two distances from my chart and make an equation showing that they are equal. Then I'm going to distribute the 1/9, and to clear the fractions, I'm going to multiply by the common denominator, which for 6 and 9, the smallest one is 18. I could use 54, but 18 is the smaller. So 18 times 1/6 becomes 3 times X. 18 times 1/9 becomes 2 times X. And 18 times 1/9 is just 2. Now I'm going to subtract 2X from both sides and get X equals 2. Well, let's go back to the chart and see what X represented. X was Mike's time. So this tells me that Mike is going to travel for 2 minutes. Alright, now I need to go back to the problem and see what the question was. The first question is, how far from the start will Mike pass Dan? In other words, how far will he catch up with him? So that's asking me for a distance. And to find distance, you multiply the rate and the time. So Mike's distance, since his rate was 1/6 and his time was 2 minutes, 2 times 1/6 is 1/3 of a mile. So after he runs 1/3 of a mile, he will catch up with Dan. The second question is, how long does it take? Well, we've already answered that. It takes him 2 minutes to do that. And that's the end of that problem. Now we're going to go to problem number 53. Again, it will help if you'll stop and read the problem so you'll understand where I'm pulling this information from. In this one, you're going to be in a biathlon. You are, it says. And you're going to, the biathlon is 87 miles. And you're going to start and you're going to do part of it with running. And then you're going to finish it up with riding a bicycle. Okay? So I'm going to put up here run and bicycle. Now, let's see what we can find in the problem. It tells me in the problem that I run at 6 miles per hour. So my running rate is 6 miles per hour. It also tells me that I ride the bicycle at 25 miles per hour. Alright, now what do I know about the time? All I know is that the total time is 5 minutes. Remember, we talked about before that if you know the total and you need to split it into two parts that are not necessarily equal, you do x and the total minus x every time. So I'm going to call this one x and I'm going to call this one 5 minus x. Again, it wouldn't matter which one was which. To get the distance, you multiply straight across. So 6 times x and 25 times 5 minus x. Now this time, the two distances are not the same. What we know is that what the total distance is. So this distance plus this distance has to add up to the total distance. So 6x plus 25 times 5 minus x is going to equal the total, which was 87. Now I'm going to distribute. Then I'm going to combine the 6x and the negative 25x. Since they're on the same side of the equal sign, I combine them just like they are without changing any signs. Then I'm going to subtract 125. Then I will divide by negative 19. And x is 2. Well, 2 what? I have to go back to my chart to see what x represented. It was the time that I ran. So that's going to be 2 hours. And that's going to be the running time. Alright, so let's see what the question was that the problem asked. What is the distance of the run? Well, I know that I run at 6 miles an hour. And I do that for 2 hours. So 6 times 2, whoops, you can't see that. 6 times 2 will be 12 miles. And then the second question is, what's the distance of the bicycle race? Well, if x is 2, then this becomes 3. 5 minus 2, that's 3. So 25 times 3 is going to be the distance that we ride the bicycle. And that's 75 miles. And notice that the two of those add to 87, which was what my total was. If they didn't add up to 87, then I've done something wrong. Alright, that concludes this part of distance problems. So you should be ready to try the problems in my math lab now.